Hello and welcome to my presentation on harnessing variational autoencoders for anomaly detection. Setting up the business context, we're going to be looking at anomaly detection, which is applied in nearly every industry, or at least most of them. For instance, detecting credit card fraud, money laundering, fraudulent insurance claims, manufacturing defects during the production process, healthcare anomalies like lab results, imaging findings, and of course cybersecurity, which is what we're going to be focusing on today. And we're going to be trying to predict network intrusion and malicious activity on networks. To do that, we are going to be trying to evaluate network traffic that is abnormal. And there's a lot of that here in this data set, which originally began as an initiative from the Defense Advanced Research Projects Agency and redeveloped for a intrusion detection competition the following year, 1999, the KDD Cup. And this data has a lot of diverse network traffic with a nice imbalanced source of anomalies with over 4 million connections and a variety of features. So this is going to be good data here for benchmarking anomaly detection, and this data set has somewhat become a cornerstone for exactly that. To make these predictions, we're going to be looking at variational autoencoders as our deep learning model. And here we have the autoencoder structure that we've reviewed in class, with the encoder compressing the data into lower dimensions, and the decoder trying to reproduce that input and do its original dimension using the input from the decoder. However, we're going to be using a variation of that, whereas this latent space in between, where it's trying to detect the relationship within the hidden layers and find the relationships, we're not going to be assigning just single values. Instead, what we're going to be doing now is representing this as a range of possible values. So for instance, you can see here what kind of single value you would attribute to these photos, and is that a fair way to predict the qualities of what we're looking for? Here we have a distribution that allows us to be a little bit more flexible with that. So instead of using a single value like an autoencoder, we're going to be using the variational autoencoder. So these latent attributes, or these hidden variables, are a probability distribution. And this is going to allow us to enforce a continuous, smooth latent space from this encoder, which is sometimes called the recognition model, and the generative model of the decoder. So let's look at an implementation of that in the code right now. Here we're loading our packages and our KDD Cup data. These beginning cells here handle the naming, the labeling of the anomalies, the encoding, the scaling and normalization, as well as the separation of data into training and test sets. This is intentionally split so that 80% for training is all normal samples, and then the testing samples are the remaining 20%, equal number of attack samples and normal samples, which should be appropriate for detecting anomalies. Moving along a little bit, we have our functions defined here that are going to be used later in the model, and these will be described. For instance, the reparameterization trick allows and introduces some randomization, and we'll see at exactly what point in the model architecture here. Here we're going to be defining the sizes of our data for the model as well. The input and output sizes will be the original size because we're encoding and decoding. The hidden layers, which are the compressed, that's smaller than the original size divided by 2, and then our latent space and dimensions are 1/3 the size, even compressed further. So here we define our encoder model, where we have the inputs, the entry point of our data, moving into the dense layer, which is the fully connected layer, where ReLU is used as the activation function to introduce some nonlinearity there. These next two layers are crucial for the the VAE model, and it's going to introduce a z-mean and the z-log variance definitions here in order to define the distribution that, like we saw here, with these continuous values. And that is going to allow the VAE to do its trick. Here, the reparameterization that we saw earlier is introduced here so that there's some randomness introduced when they're generating new data points. And this also helps with the backpropagation for the algorithm too. From the encoder, the decoder is defined. Here, the latent variables, those hidden attributes, are going to be accepting as the input from the encoder. The input to the decoder is the output from the encoder. That's then passed to the dense layer, which similarly, decoding and reconstructing this data. Now we're introducing the nonlinearity with ReLU. And then finally in the output layer, we are back to our original dimension size, and we're enforcing a sigmoid activation function, which is going to give us a binary predictor of yes, abnormal, or no, not abnormal. So here we define our atom optimizer, we make some predictions, we have some good precision, and we move down here to see the scatter plot of the encoding here. And we see the initial assumptions that when we introduce a threshold, show these predictions, which orange is actually the anomalies here. And we see that it does a fairly good job, but there is some space that is left remaining there. So that is the presentation. Thank you.